So now we are in the last part of our series in linear response theory, the introductory part, and then we will do an application part, and today we're concerned with the Kubo formula. Now, to do this, let's recall the following. A given quantum system can be represented by the following Schrödinger equation: H0 plus W of t, which is, this operator is written in the Heisenberg representation acting on psi of t, equal to I h bar d psi of t dt. Okay, now here H0 is a Hamiltonian for which we know its ground state, so its ground state known. And W of t in the Heisenberg representation is a perturbation. And as we did in the past two videos, what we want to do is to determine the response, or determine the quantum state psi of t in an iteratively way as a function of powers, or product of powers of W of t evaluated at different time instants. So now what we want to focus on is on the linear expression to calculate psi of t in terms of W of t. Okay, so then now it is useful in this type of problems that we work on the interaction picture. So in the interaction picture, we get rid of H0 and we only have W sub I of t, which is written in the interaction picture as we did in the past video in the interaction picture, or 3 videos ago where I explained interaction picture. This acts on a new state phi of t and is equal to the evolution I h bar d phi of t dt. Okay, now how that happened? So that happened because in the first Schrödinger equation we assume the following ansatz: e to the minus I h bar h0 t times phi of t. So that means that this quantum state evolves according to the free Hamiltonian, or to the Hamiltonian for which I know its ground state, and then everything is written now in terms of this new quantum state phi of t. And this phi of t, as I said in the previous lecture, can be written iteratively in terms of a successive or a series of sums that are contained in the scattering matrix, with the knowledge of this state at minus infinity. Okay, so then this scattering matrix can be given to an arbitrary order n by the following expression: n factorial I h bar to the power of n. Now, successive integrals from minus infinity to t dt1 minus infinity to t dt2 minus infinity to t dtn, okay, of the time order product of the perturbations at each of the times given by the integrations here. So W sub I of t1, W sub I of t2, W sub I of t Tn. Okay, now in the problem of linear response, what we're dealing with is with the following question. So we have a perturbation W sub I of t, which is equal, we already showed this, it's equal to e to the delta t divided by v integral of d3r prime, some sensitivity function r prime t times some operator b sub I of r prime comma t. So then the excitation or the perturbation in this system is associated with the operator b sub I. Okay, now that excitation or this perturbation has an associated response in the system that we're going to label as or that we're going to associate. So response, let's write like this: response is associated with operator A of R comma T in the interaction picture. Okay, this is interaction picture. Now what we're going to do is that we're going to do the following. Let's say that we want to associate this response with this excitation. What we will do is that we will start by considering the expectation value of this operator first in the of course in the Heisenberg picture, where we have the state psi of t representing the quantum state of the system. Okay, so then we write expectation value of A is equal to first order in psi by the following so bracket operation psi of t A sub r psi of t to first order. Now if we replace what we said psi of t is equal to, which is e to the minus I over h bar h0 t times the state phi of t, then what we end up with is the following. So we have to first order phi of t here, we have here e to the I over h bar h0 t, here we have a r, which can have some just time dependence, but I'm just going to assume that it doesn't, but it can have some time dependence, and because it can be written in the Heisenberg picture, but we're going to write it now in interaction picture. And here we have this state is just the same as I have here, so this is e to the minus I over h bar h0 t phi of t. Okay, so then, and this is nothing but to first order phi of t a sub I of r comma t in the interaction picture. Now this is the first order as well, and now this acting on phi of t to first order. Okay, now what we can recall is that phi of t, we already said that phi of t, let's write it here, is written to first order as 1 plus 1 over I h bar integral from minus infinity to t d tau w sub I of tau, while acting on phi of minus infinity. Okay, so then we replace that thing here, and what we have is that to first order, then we write the following: phi of minus infinity. Okay, here we have 1 minus 1 over I h bar integral from minus infinity to t w sub I of tau d tau Okay, here we have a sub I of r comma t operator, and here we have 1. Now we're replacing for this one, plus 1 over I h bar minus infinity to t d tau w sub I of tau phi of minus infinity. And so then we just have to expand this a little bit. So then here this is 1 times a is a times 1 is a, so then the first term we have here is phi of minus infinity on the operator a sub I, and this on phi of minus infinity. This first term here, I will say that this is the expectation value of a sub 0. Okay, so then this is just the expectation value of our operator, with the knowledge of phi of minus infinity without any perturbation. Now we continue with the other terms here. So we have the following. So we have this phi of minus infinity, which is acted upon by this minus 1 over I h bar. So then if I put this I upstairs becomes positive, and if I put this I upstairs here becomes negative. So what I'm going to write is the following. So I will say minus 1, so minus I over h bar. So with this acts here, and this multiplies by this 1, because we're not going to consider the quadratic term here, which is what will happen if I multiply this term here by this operator and then by this other term here. So instead, what I'm going to do is the following. I'm going to multiply this term here by this a sub I here just by this 1, and on the other hand I'm going to multiply this term here by this ai here by this 1 here. See, so then I have the sum of two linear terms in the perturbation. So then first, this is here when I put this I here becomes minus. So then I write minus I over h bar. See, the integral from minus infinity to t. Okay, what comes first? So first comes the operator. So this is I sub a sub I of r comma t w sub I of tau. See, sorry, I forgot the state. So then I have to write first the state. Phi of minus infinity a sub I of r t w sub I of tau phi of minus infinity, and all of this d tau. So then, and the second term that we have here, we have this term here. When we put this I upstairs becomes a plus, and then here the perturbation comes first and the operator comes later, and both of them are sandwiched between phi minus infinity and phi minus infinity. So then I write plus I over h bar integral from minus infinity to t phi of minus infinity w sub I of tau a sub I of r comma t acting on phi of minus infinity d tau plus corrections of second order, which is what will happen if I multiply this term here with this term here, will give me products of the perturbation at different times. Okay, so now I'm left with the following. So let's scroll down a little bit. So I will write this. Remember that we have this thing here. Okay, we cannot forget that. So then I will write now in black that the expectation value of A, which depends on R and T, okay, will be equal to A sub 0, which is what we have here, minus what we have here plus what we have here. Now, I can factorize these two expressions. So then first I write minus I over h bar, integral of minus infinity to t. And so I write this minus this. And you can just note that this minus this is just the commutator between AI and WI. So then I write the following. Phi of minus infinity. Commutator A sub I of RT with W sub I of tau of phi of minus infinity all d tau. Okay, so that's what we have, and then we define a quantity called delta sub A of RT. This is a scalar. So then this is the expectation value of this operator and of this operator. So now this is a scalar because it's the difference between these two expectation values. Minus the expectation value in 0. And we have that this is equal to minus I over h bar, integral from minus infinity to t d tau, state phi of minus infinity, commutator A sub I RT B sub I, sorry, not yet. So then W sub I of tau. We close the commutator and we operate on phi of minus infinity. Okay, so this is the very basic step that we need to do. Now what we have to do is to specify this perturbation is associated with B sub I of R prime comma T or comma tau, in which way. So then first we say that the perturbation W sub I of tau is equal to E to the delta tau divided by B integral d3R prime, of course from minus infinity to plus infinity, of some sensitivity function f of r prime comma tau times the associated operator B sub I of r prime comma tau. Okay, so then this is what we have, and when we replace this here, then we can say that delta A of R T is equal to minus I over h bar integral from minus infinity to t d tau, okay, phi of minus infinity. I open the commutator A sub I of R comma T, commutator with E delta tau divided by B integral minus infinity to plus infinity d3R prime f of R prime comma tau B sub I of R prime comma tau. I close the here I close the expectation value, and then I operate on phi of minus infinity. Okay, now what can I do is just to I want to do the following, so I can of course remove the integral outside the expectation value, the commutator. So the commutator at the end will only be calculated between these two operators, because everything else is a scalar. So between AI and BI, okay, everything else is a scalar. So I just write minus I over h bar integral from minus infinity to t d tau, integral from minus infinity to plus infinity, here d3r prime divided by b. So then I got rid of this too. Now what else do I need? So then I have here I'm left with the expectation value based on phi of minus infinity, commutator of a sub I of r comma t with b sub I of r prime comma tau, close the commutator, times phi of minus infinity times e to the delta tau times f of r prime tau, which is the sensitivity function of the perturbation. Okay, so then now we are left with the following. So we're almost done. So then I'm going to adopt now some form to calculate this expectation value. Okay, so this amplitude, which is the following. I'm going to adopt the some equilibrium ensemble to do that. So then in the equilibrium ensemble I can pretty much write this expectation value here in the following way. So phi of minus infinity a sub I of r comma t comma b sub I of r prime comma tau, expectation value phi of minus infinity. So expectation value, this is a ket, phi in minus infinity, so this is equal to 1 over z, the partition function, summation over n e to the minus beta en. Okay, phi n, which are the associated eigenstates for each of the energies, a sub I of r comma t b sub I of r prime comma tau, close the commutation relation, act upon or acting on the ket of phi sub n, and this I will just simplify in the following form. I just say that this is just this expectation value of a sub I of rt and the expectation value of this commutator b sub I r prime tau. Okay, so I will just adopt this this notation and I will replace it here to simplify things. Okay, so then I just draw this line here, so that is just equal to minus I over h bar. Let's use red because I don't know if you can actually see this orange here. Minus I over h bar. What else? Integral from minus infinity to t d tau. Integral from minus infinity to plus infinity d3r prime divided by v. Okay, expectation value of the commutator between the two operators, now this at r prime comma tau times e to the delta tau f of r prime comma tau. So then there's this question, like what else can we do with this? So there's one small thing that we can do, not very much, but what we can do is, if let's say we want to have both of these integrals to minus infinity, but the integral only goes up to t. So that means that when the integration variable tau is greater than t, we have to impose a restriction that for that limit, so for tau greater than t, the integrand must vanish. Okay, so then we're going to impose some restriction in order to go from minus infinity here to plus infinity here, but complying with this restriction. And that is done in the following way. So this is from minus infinity to plus infinity, the tau from minus infinity to plus infinity, the 3r prime, and here I write theta of t minus tau. That means that when tau is greater than t, then all of the thing will vanish. Here, this is the expectation value of the commutator between both operators, b sub I of r prime comma tau, close the commutation relation and the expectation value, times e to the delta tau f of r comma tau, okay, r prime. So now I will define the following: some Green's function, g sub a b retarded of r minus r prime t minus tau, given by so that Green's function will be given by the following. So let's use dark blue. So GAB retarded of r minus r prime t minus tau equal to minus I over h bar here. Now this theta of t minus tau, expectation value of a sub of the commutator between a sub I evaluated at r and t with b sub I evaluated at r prime and tau, close commutator close expectation value. So then, and now this will give me the following expression for the response delta A of RT equal to the integral from minus infinity to infinity of d tau integral from minus infinity to plus infinity of d3r prime over v of the Green's functions GAB retarded or r minus r prime t minus tau times e to the delta tau f of r prime comma tau, where this f is just the sensitivity function to the excitation associated with operator B in the perturbation Hamiltonian. So then this G is what it's called in let's say in some other fashion chi AB of r minus r prime t minus tau. This is called Kubo susceptibility. Okay, and this formula that you see here is what is known as the Kubo formula. For linear response. Okay, and then of course there's great things that you can do with that. Let's just write it again in terms of this now chi, which is a susceptibility, because this is a, you can see in quantum mechanics, if these operators are, let's say, one particle operators, this is a two, this will be a two particle Green function or a two particle propagator. So then it's much more precise to call it a susceptibility. And this is this formula, that susceptibility of chi AB. So that means chi of A given B. So given the excitation B of R minus R prime T minus tau is equal to minus I over H bar theta of T minus tau, expectation value of the commutator AI BI, and this is known as the Kubo formula for linear response, or Kubo formula for susceptibility, where this is just the Kubo susceptibility. So then now the things that we can calculate with this and how useful this is, you can think about spin, susceptibility. You can think about conductivity, polarization. So many things. Polarization. Many things can be calculated with the Kubo formula. And the thing that you should keep in mind when you do all of these things is that the response, that means the response associated with operator AI, will increase linearly with the excitation associated with operator BI. That's why it's called linear response. Okay, now if you want to go beyond this, of course you can beyond this, but then you will have to expand, or you have to use, let's say, phi of t, let's say the correction to second order or the correction to third order, and then you will start adding complexity to the model, but that's not what we're dealing with now. So we're just up to linear response. So then in the upcoming videos I will discuss these applications: spin, conductivity, polarization, and what can you do with the Kubo formula. For now then, that's all, and thanks for watching.